Hello, my name is Joshua, and for my project, I chose hardware optimization. Machine learning takes a lot of power, and especially in embedded systems where this is a limited resource, it is crucial to increase the power area efficiency. A lot of the power consumption comes from the multiply accumulate function that happens hundreds of thousands to millions of times per forward pass of a network. Stochastic computing introduces a way to simplify this to a single XNOR gate for multiplication versus the binary counterpart, which is a complex circuit. The input weights and the feature weights are sent in to an XNOR gate, and then the output of the XNOR gate is summed, and you can then normalize that and use that for the multiply accumulate function. The architecture proposed involves simplifying the random number generation. So a lot of stochastic computing requires highly uncorrelated bit streams, which requires several random number generators. My approach to solving this that I was intrigued by was we know machine learning is able to overcome patterns, was to try to train out the bias introduced from using a single random number generator. The current implementation was shown to have 2.5% power efficiency savings over a traditional multiply accumulate. And it's also important to note that the communication on the FPGA I used, which is an AMD /Xilinx board, requires something called the AXI interface, which is shown on the left. The AXI interface introduces a lot of overhead, especially when we're only using a single. So the original idea was just to implement the multiply accumulate function, but the overhead introduced with the AXI interface there would be worse if you wanted to add a ton of them. So instead, I made the entire layer in HLS. So there only needed to be one AXI interface to send an entire burst of data one time and then read it back out instead of doing it over and over again. Also, when I measured, sending the data from the CPU to the FPGA fabric took way more time than anything else. So you only want to have to do that one time. So the final implementation has the entire layer in the HLS code, which is a separate block. The model was verified in two different ways. So the model was trained in Colab Python for more computation, and the custom gradient and the custom layer was meant to model the hardware architecture, and that was how it was verified that the accuracy, that it is feasible and that accuracy was preserved, and the model was able to overcome the noise from quantizing the model. I was only able to implement a dense layer. The convolutional layer was much more challenging, but even with just the dense layer, it was shown that the model was able to outperform the binary model being trained on the same amount of epochs with all the rest of the settings were the same. So this was a really fun finding, and this proved that the model would be functional. And then from the bottom up, working on the hardware, when compiled, it was shown that the model could run at 300 megahertz, which is much higher than the board is even rated for. So that is not a bottleneck. And the latency is higher than the binary counterpart, but that is due to the stochastic computing in general has higher latency but lower power. So it's a trade-off. There's no free lunch. The challenges I faced when trying to use the model that I verified on Colab on the board was the block design in Vivado, which is shown below, has there's very specific ways to use the memory for the AXI interface and the communication between the processing system and the programmable logic. And I was not able to get those to work because the address blocks were fighting with me, and that's where the crossover stopped. But the model showed in Colab Python that it is possible, and there's also some strategies that I have once it's implemented on the board, if it ends up collapsing, to slightly modify the random number generation to more closely represent what Python does. when it was running the forward pass and for training. Um, I had a lot of fun with this project. I hope that I was able to, at a high level, explain all of the concepts that were used to train this network and how this how this model learned to overcome the bias introduced from the stochastic computing. But yeah, I hope it made sense at a high level, and thank you for listening.